So we were discussing about the Jordan canonical form, and the idea is you have T, which is a matrix comprising of generalized eigenvectors. You do T inverse AT, you get something where you have lambda, 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 assuming these are all repeated eigenvalues, something like this. So you have one block which looks like this, and you could have multiple blocks of this kind of matrix where you have 1 in the off diagonal term, lambda along the diagonal term, and then 0 thereafter. We said that this matrix looks very similar to lambda plus 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 and so on. So you have 1 in the off diagonal term, like right above the diagonal term, and then you have 0 everywhere else. And this matrix is, of course, lambda times I. This matrix is given by n. And we wanted to figure out what is exponential of A. So I'm going to multiply it by T inverse and T, and I get exponential of lambda I plus n. These two matrices compute. So this is exponential of lambda I times exponential of n. Okay, this is where we had stopped in the previous lecture. This is what we wanted to do. This equality is because lambda I and n commute. Okay, and today my goal is to tell you what this particular expression looks like. What is exponential of n? And what I'm going to, so there is a specific property that n has. So let's try to study what that property is. So you've seen this particular matrix. What do you think would be a property of a matrix of this type? Yes.
Multiply it by itself, it should just shift the rows down by 1, right?
That's not down, but it will shift it up by 1. So let's look at n equals to 0, 1, 0, 0, 0, 1. This is something that we can do by hand. So what is n square? That's 0, 1, 0, 0, 0, 1, 0, 0, 0. So I'm just doing an example, but the property still remains. So this is, I get 0, 0, 1, 0, 0, 0, 0, 0, 0. So this is the kind of behavior that you will see in n square, where this off diagonal term with 1 will shift up by 1. So you will have 1 here, and then you will have 0 everywhere else. So if n is of dimension n cross n, then n raised to k equals to 0 for all k greater than equal to n. That's the property. Okay, any questions so far? Yes, you have a question? No, okay. Okay, So now, generally speaking, we are more interested in exponential of AT. So what would be exponential of NT? So I think, so now you can compute exponential of N fairly easily. It's identity plus N plus N square over 2 factorial plus N raised to N minus 1 over N minus 1 factorial. Because everything else, all the other higher order terms are 0. So this is what the exponential of N looks like. We are more interested in exponential of NT, and that's given by IT plus NT plus N square T square over 2 factorial. Oh, I doesn't get multiplied by T. Yeah. So it's I plus NT plus N square to T square over 2 factorial plus N raised to N minus 1 over N minus 1 factorial T raised to N minus 1. So this is what the exponential of NT is going to look like. And so let me just write down the expression. This is going to be 1, 1, 1, 1, 1 along the diagonal, T, 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 T along the off diagonal, T square over 2 factorial, then T cube over 3 factorial, and so on, all the way up to T raised to N minus 1 over N minus 1 factorial. Because remember, each of this matrix N contains only 1. So essentially, it's just T square over 2 factorial at appropriate locations within the matrix. So T raised to K over K factorial is what you have to put within the matrix. And it's going to be 0 in the lower diagonal term. Okay, so it's not too difficult, but I think this is the most general form. So remember, you can either diagonalize the matrix A, in which case the matrix exponential is very easy to compute. But if you cannot diagonalize, you can always convert it into a Jordan canonical form. Once you convert it into Jordan canonical form, you will have this exponential of lambda I term multiplied by exponential of NT term. So this will be lambda IT, and this will be exponential of NT. Exponential of NT is given by this expression. Exponential of lambda IT would be a fairly simple expression. And so you have to multiply the two matrix and you get T inverse exponential of ATT. Okay. So with this framework, you can compute the exponential of AT for any matrix A, because either you can diagonalize it or you can convert it into Jordan canonical form, and then you can solve this problem. So in general case, you will have T inverse AT, J1 0 0 0 J2 0 0 0 J3 and so on, and T inverse exponential of AT capital T equals to exponential of J1T exponential of J2T and so on, 0 0. So in the general case, you might have multiple Jordan blocks, you might have multiple diagonal blocks, depending on whether you have generalized eigenvectors or regular eigenvectors. And then you can do the exponential of each of these Jordan blocks or the diagonal blocks, and you get the expression of exponential of AT, pre multiplied by T inverse, post multiplied by capital T. So that's the theory of computing exponential of AT. So now if you have a complex control system, you have a battery pack, you have a robotic manipulator, you have a complicated humanoid robot, as long as you can write the dynamical expression for that as x dot equals to 8xt, then in order to compute what the trajectory of the system is going to look like, you need to compute exponential of AT, and this algorithm will allow you to compute the exponential of AT fairly quickly on the embedded devices that you're going to use for trajectory planning on that hardware. Generally speaking, you have a highly nonlinear system, in which case you tend to linearize it for the next 5 milliseconds, next 100 milliseconds, next 5 seconds, or next 1 minute, depending on the application. And then you compute the matrix exponential for those many milliseconds or microseconds or seconds or minutes or hours, depending on the system at hand. We did talk about linearization of nonlinear systems, right? And you've done some assignments, so you know what that process looks like. Any questions so far? How many of you have encountered linear systems in your previous birth or whatever, like previous life? Few of you? Okay, perfect. Now you have a very powerful tool at your hands, at your fingertips. I want to do an example, continue our expression for the matrix that we were talking about in the previous class. So my matrix A equals to 2, 1, 0, 2. My T actually turns out to be the identity matrix, because remember the generalized eigenvectors for this was 1, 0 and 0, 1. So I'm going to keep it as an identity matrix. So what is T inverse AT? 2, 1, 0, 2. It's the matrix itself. We did the derivation of generalized eigenvectors in the previous lecture. So I'm going to refer you to the previous lecture for where we get this 1001 from. So the exponential of AT is equal to exponential of 2t 0 0 2t times exponential of 0t 0 0. Can someone tell me what is this exponential of this matrix? Exponential of this matrix. Yes, please. Perfect. What about this matrix? Yes.
1, 0, 1.
Perfect. That's right. Oh God, now I have to multiply this. I have exponential of AT. Now I have a linear system, x dot t equals to axt, x of t0 equals to 2, 3. What is my phi of t? T naught x naught, the solution to this differential equation. So that would be exponential of a t minus t naught x naught. Whatever that number turns out to be. Okay, I guess let's just do the calculation. Why leave it at this stage? So this is 2 times e raised to 2 t minus t naught plus 3t e raised to 2 t minus t naught plus 3, and then it's 3 e raised to 2t. Oh, 2t minus t naught. Oh, you know what? I think I need to do t minus t naught here too. So everywhere I should have t minus t naught. Perfect. Did I make any other mistake? No. Yeah, it looks correct. Yes, please.
Like on the top right side, why is it t equal to t instead of t equal to t plus 1 plus that means by that row with that column?
Oh, there shouldn't be any plus 1 here, right? That's what you were saying?
Yes.
Yeah, okay. There should not be any plus 1 here. So there won't be any plus 1 here. So there won't be any plus 3 here. Thank you. It means you are not sleeping. Yeah, okay. Okay, so this is how you compute the solutions to a solution to a differential equation. So if I had asked you how to solve this particular expression, how to solve this differential equation 4 weeks ago, you would have said, I don't know, but now you know. Okay, and now you will remember this till the end of your life, which is a good thing. That's why we get our degree, because then we don't forget. Awesome. Any questions so far on this? Okay, if you have multiple Jordan blocks in this T inverse AT, then you have to look at each of those Jordan blocks separately. You'll have to do this computation for each of those Jordan blocks, and then you can do the appropriate computation here in order to compute the solution to the differential equation, linear differential equation. So what I want to spend some time on is to understand the properties of this matrix exponential. So let's do that. Can I erase this side of the board? So this is this material, the properties of matrix exponential, comes from chapter 3. 3.2.2. So let's talk about these properties. And so I want to remind you phi of t naught is exponential a t minus t naught. And I'm going to denote by psi of t exponential of at. So the first property is phi of t naught psi of t naught inverse. For all t and t naught. So phi of t and t naught will always be invertible. Remember, phi of 0, 0 is actually equal to identity matrix. So no matter what value of t and t naught you pick, it's going to be invertible matrix. The third one is called the semi-group property. I know we haven't talked about group theory here in this class, but this is known as semi-group property. T tau equals to phi T sigma phi sigma tau. So let me tell you why this semi-group property is important. Okay, so what is semi-group property? I start with x naught and I go until, so I start with x naught at time tau, I go until time sigma, that becomes my initial condition for starting at sigma and going until time t. It's the same thing as starting with x naught at time tau and going all the way up to time t. That's the semi-group property, and all you have to do is multiply these two matrices and you know what the position is going to look like after the sum of sigma minus tau plus t minus sigma time step. Okay. Yes, please.
So like, can we just iterate from tau to t?
Sorry.
So can we use this as an iteration method?
Definitely. I mean, that's the whole purpose. I mean, that's the benefit you get in a linear system where you run the linear system for a certain amount of time, multiply it by the next matrix, and you get what the linear system position is going to be at a future time step.
How do we choose the step length? Like, how do we choose this amount? This step?
I didn't understand what do you mean by stabilize. So the system is either inherently stable or unstable. So there is no way you can stabilize it. We're not talking about the one with control. So we'll talk about the controlled case somewhat later.
I had something in mind, like something like sampling.
Yeah. So for instance, suppose this is 1 millisecond. So you have phi for 1 millisecond. You want to figure out what happens after 10 milliseconds. You just multiply phi 10 times. You get the transition matrix for 10 milliseconds duration. Okay, that's what the semi-group property is saying. In nonlinear systems, all of this would be nonlinear functions, but because we are in a linear system setting, all of this is just matrix multiplication. And for any microcontroller, matrix multiplication is order of magnitude easier than running an ODE44 on that microcontroller and expecting it to give you a solution in a matter of a few seconds or milliseconds. Okay, the fourth property is phi t naught inverse is phi t naught t. What's the benefit of this particular property? So I have xt equals to exponential at minus t naught x naught. If I want to figure out x naught, so I'm standing at time t, I'm looking at my current xt, I want to know what happened in the past. Okay, so how do I know what happened in the past? I'm going to just invert this matrix. I'm going to get exponential of minus a t minus t naught xt, that will be equal to x naught. So this is just a matrix inversion that I'm doing. But the cool thing about matrix exponential is that the inverse of exponential is just exponential of the negative of the same matrix. Exponential of at1 exponential of at2 equals to exponential of a t1 plus t2. And this property, of course, you will recall, because at1 and at2 commute, so the multiplication of matrix exponential is the same as exponential of the sum of the matrices, because they commute. Sixth property, a exponential at exponential at times a. Okay, so these are the properties of matrix exponential. I'm sure you can come up with more properties of matrix exponential based on these elementary properties. But these properties would be useful when we are doing the analysis for linear systems in the future. Any questions so far? All of these properties follows from the expressions that we have computed. Oh, let me write down the other one, seventh one. We have used it extensively so far. It's not there in the book as a result. But if you have T inverse exponential of AT for any matrix, for any invertible matrix T, so it doesn't necessarily have to be the matrix of eigenvectors or generalized eigenvectors. It can be any invertible matrix. This condition will hold true. So this one is not there in the book, so I'm writing it down from some stuff that we did in the class few days back. Okay. No questions? I want to mention a theorem because we'll probably try to prove it in the next class. The time is about to get over, so I'll just write down the statement. The solution space of x dot t equals to axt, xt naught equals to x naught is a linear vector space with dimension n. And let me tell you why this is an important property. When we prove it, you will realize that it's actually pretty trivial and follows from the property of linear systems. But it's a very interesting property. So remember, I'm solving an ordinary differential equation. When you're solving an ordinary differential equation, and remember, x naught could be any initial condition. So I have an ordinary differential equation. I can start from any initial condition. I'm going to get a trajectory. It turns out that the trajectory that you get has a dimension n. All the set of trajectories that you can get has dimension n. And it's interesting because technically speaking, without knowing this, all I can say about this solution is that it's going to be a continuous function of time. That's it. All I know about this space is that this is C of, let's say, maybe I don't even want to write it as T naught. I'll write it as R to Rn. That's what I know about this. If I erase this part, if I do not show you this part, this is an infinite dimensional space. Okay, the space of continuous functions that takes as input time and outputs a vector in Rn. That's an infinite dimensional system. However, the cool thing here is that if you look at the solution space for this differential equation, it's actually a n-dimensional object within this space, within this infinite dimensional space. You cannot say this for nonlinear systems. Okay, so if you have a nonlinear system, you can start from any initial condition. You can have completely different behavior, and therefore the solution space of nonlinear systems could be infinite dimensional. Okay, but in the linear case, it is finite dimensional, and not just finite dimensional, it is actually of dimension n. And that's the cool thing about this vector space. Let me write it as dimension at most n. You could have a situation where A has a lot of zero entries, in which case you will have a dimension lower than n. But in the case where A has n eigenvalues, and those are non-zero eigenvalues, in which case the solution space will have dimension n. So we are going to prove this result in the next class. And then I'm going to talk about modes of this dynamical system. Modes is another important concept. You must have played guitar, or you must have seen other people playing guitar, and guitar has modes, and so does linear system. So we'll talk about what the modes of the linear system looks like, and then we'll move on to the next chapter, which is chapter 4, where we talk about stability of linear system. So next class, we'll prove this theorem, we'll talk about modes, we'll understand what the physical meaning of modes mean, and then we'll talk about stability. Thank you.